Hey everyone. Today I am presenting our work on 4D generic video object proposals. This is joint work between Alyosha Shep, Paul Voigtlander, Mark Weber, Jonathan Luton, and Bastian Leiber. To navigate around the world, robots need to detect and track objects. The most common vision-based approach is tracking by detection. However, in robotics, it is also important to localize object trajectories in 3D space. We are able to train detectors for cars and pedestrians, as we have a lot of labeled data. But how about this child stroller, or any other number of unexpected objects that a robot could come across? Tracking by detection assumes that we have an object detector for every object we want to track. In a standard vision and robotics pipeline, we now need to collect labels for child strollers and train the detector to detect these. Robots experience a continuous stream of sensory data in the 3D world. This is very different to typical datasets with distinct samples of observed classes. Robots need to be able to operate in an open set world with completely unknown dynamic objects. This is not just an academic problem. Teslas have crashed and people have died because of a failure to recognize a fire truck. In any practical application scenario, we can expect the frequency of object category observations to follow a power law distribution, with some object categories occurring very frequently and the vast majority being increasingly rare. We will never be able to learn a detector for every class. Thus, we need to be able to mine objects from input data and learn from experience. How do we go about this? Well, in traditional multi-object tracking, trackers are initialized based on object detections, such as faster RCNN. However, in order to track any generic object, we need a similar localization to start tracks. Here, traditional methods have been used for generic object proposal generation. However, all of these are too low precision. E.g., as seen in the bottom plot, they need approximately 1,000 proposals to cover 60% of relevant objects. Visually, to cover both rider and horse, we need to spawn a jungle of proposals, as seen in the bottom right plot from Cho et al. We propose a different approach. The key ideas of our method are as follows. First, we use a large-scale dataset to learn to segment and score per frame cues. Second, we associate and rank these object tracks over a video. And third, we make use of parallax as a cue to identify temporally consistent object tubes under ego motion of the recording vehicle. To obtain object cues, we train mask RCNN in a category-agnostic setting on a large-scale dataset. By only differentiating between objects and non-objects, mask RCNN learns to generalize better to unseen objects, as we experimentally validate. Different to RPN outputs, we also obtain segmentation masks, which are essential for precise data association. Several object classes are observed during our model training. To retain information about these classes, we add another fine-grained classification head that provides us with object class information for 80 object classes observed during training on COCO. From this network, we get mask proposals with corresponding objectness scores and precise semantic info for some classes. These are the inputs to our track miner, in addition to stereo video, which we use to localize these masks in 3D space. We mine tracks as follows. From every proposal and every frame, we perform backward-forward data association. This association is guided by the estimated sparse scene flow and track motion model. We compute an association score by unprojecting track masks to 3D, applying the estimated 3D motion model to the object point cloud, and then projecting the object point cloud back to the image. Proposal to track fit is evaluated under the motion model in 3D space and mask consistency in the image domain. These two quantities are implicitly coupled. As a result, we get several track proposals, tightly overlapping in 3D space. We score these tracks under motion consistency, temporal mask consistency, and evaluate sequence-level objectness using the network estimates. We perform additional optimization steps that select the best scoring object track hypotheses that do not overlap in 4D spacetime significantly. This optimization procedure takes semantic knowledge implicitly into account via the track scoring function. We select a subset of object tracks using the following CRF model. This model contains a unary term for each track tube, as well as a pairwise term for the interaction between the tubes. The score theta, the unary score theta, for each tube tau is a linear combination of the tube's motion score, its mask consistency score, and its objectness score. The pairwise function penalizes the overlap between two tubes, e.g. the 3D IOU. We rank video tubes using the log likelihood ratios between the proposal tube and the null hypothesis tube. The null tube encodes tubes generated from random background clutter. We model this according to a multi-hypothesis tracking framework. For more details, please refer to the paper. So, how well can we track? We perform clear-knot evaluation on car and pedestrian categories on Kitty, using the extra semantic information output by our network. Our approach performs on par with stereo-based tracking by detection system CIWT, using the same inputs. CIWT has a higher motor because it can also track objects at a far distance outside the range of stereo depth. Our method performs significantly better compared to previous category-agnostic trackers, with far fewer ID switches and a higher motor score. This is important for object track mining, as we don't want fragmented tracks. Our method also produces accurate 3D localization, as shown in the plot in the top right. Visual examples of localized known objects can be seen at the bottom, visualized into a stereo point cloud. However, the question remains if we can generalize to unseen objects that were not seen during training. Yes, we can. In order to show this, we sampled short video snippets from Oxford Robocar dataset and labeled objects in the middle frame that do not overlap with the 80 COCO classes. We want our tracker to have as high recall as possible, with as few proposals as possible. Here, we can see the results of our method. The solid curves are the proposal networks which are run per frame. The dashed curve is our sequence level proposals. Everything except mask XRCNN is trained on only the 80 COCO classes. However, mask XRCNN is trained on COCO and Visual Genome, which is more than 3,000 classes. This is why mask XRCNN has better precision. Our category-agnostic mask RCNN performs better than both sharp mask and the original mask RCNN. Also, our approach matches the unknown object recall of mask XRCNN, despite only using the knowledge about the 80 COCO classes. This is impressive, as we train on much less data and achieve similar results. Can we generalize to unseen classes? Yes, we can. In this video, we see the frame-level object proposals in the top and the sparse scene flow used for guiding the data association in the bottom. Now we can see all proposed tube tracking results, visualized as both 2D boxes above and 3D boxes below. Here we show only confident objects, those belonging to classes seen during training, in both the image domain and the stereo point cloud. Finally, we show the same visualization while displaying all objects, those belonging to both known and unknown object classes. Thank you for paying attention to our talk. Code and data are available, and we highly recommend you read our paper if you're interested. Thank you again.